Hello everyone. So let's start the session for today. So welcome to session 2 of Summer of Robotics on Mechatronics from perception to action. In the previous session, we covered what is mechatronics. We learned about CADing. Then we got into the maths of things where we learned about coordinate frames and transformations. And we ended the session with inverse and forward kinematics. So let's discuss what we learned today. So our problem statement for today is that we have a Mars rover that has landed on an unexplored region of Mars, right? So let's now look at what all it has to do. It has to collect a very special rock and bring it back to its base. But the thing is, because of communication lag between the rover and Earth, it will have to make all of its decisions on its own by using its sensors, estimation algorithms, and its actuators. So let's look at this problem in detail. The rover will first have to detect the rock. This is where we will learn about detection sensors. Then it will have to determine its displacement. This is where we will look at encoders in IMU. Then it will have to precisely determine its location. This is where we'll study about odometry and Kalman filter. Then we have to make sure that it reaches precisely. Here we will learn about control theory and PID. We will also look at some of the dynamics that the rover will have to face. And then it will pick the rock using its actuators. So what makes this mission so particularly difficult? As you can see, the terrain of Mars is really rocky and bumpy with a lot of obstacles. And it also has a lot of craters. So we need to make sure that the rover carefully calculates its path so as to reach the rock safely. So let's look at challenge number 1. The rover cannot see distance. The camera on the rover can only detect the rock, but it gives no details, like how far away is the rock? What if there is any obstruction or a crater in between? And is the rock actually reachable in its current path? This is where the rover will use its sensors. So it uses its sensor to perceive its surroundings. Now there are two types of sensors that it could use. The first is depth camera, where this captures the distance of the object by creating a 3D map. And the second kind that we have is a LiDAR. Now this is an active remote sensing technology that uses pulse lasers to measure ranges and distances. Okay, let's look at depth cameras. So the first kind of technology that depth cameras use is time of flight. This is where the camera will emit a pulse of infrared light. And what happens is this light falls onto the object and gets reflected back. Now, since we know that the speed of light is constant, it can be used to determine the distance of the object by multiplying it with the time and dividing by 2 because the light had to travel both ways. So, time of flight technology is best used in applications where speed is a must. So, it gives us real time measurements. It's used in gesture recognition and in autonomous navigation. The second kind of technology that we have is structured light. Now, what happens here is, unlike the case of time of flight technology, where the camera projects pulses of light, here it projects a grid of infrared light. So this forms a sort of dot matrix that falls onto different surfaces, and then this grid will deform and warp around these different surfaces, which is then used to be converted to distance by using some very sophisticated algorithms. So this is best used in applications where we're looking at distances in close ranges because these give us very highly detailed 3D scanning. So an example of this would be facial recognition. The third kind of technology that depth cameras use is stereo vision. Now, this works very similarly to how our human eyes work. So we have two cameras that are separated by a few centimeters. What they do is they focus at the same point. And how we calculate the distance is by something called triangulation, which is basically creating triangles, measuring angles, and then determining the distance. So this is best used in robotics, in outdoor environments, and in industrial guided vehicles. Does anyone have any doubts so far? You can raise your hand if you do. Okay. The second kind of sensor that it can use is LiDAR. Now, LiDAR stands for light detection and ranging. So, LiDAR also works on the time of flight technology that we discussed in depth camera, right? So, first, the step is emission, where the sensor will project thousands to millions of pulses of laser light into the surrounding. These then get reflected by the objects, which is then used to calculate the distance. So, how does LiDAR ensure that it is mapping all the surroundings? So it can either rotate the sensor or use multiple oscillating mirrors to sweep the laser beam. And then this lets us obtain millions of coordinate points, which are then compiled to give a 3D point cloud. And then this is used to provide us with a detailed real-time model of the environment. So now using these sensors, the rover was able to scan its surrounding and it estimated the rock to be about 12 meters away from it. This brings us to our challenge number two, that the rover doesn't know where it is. So now that the rover is not on Earth, it cannot make the use of facilities like GPS. So how does it know how far it has moved, which direction it is facing in, and what if it has undergone some sort of drift? This is where encoders come into play. So an encoder is a type of sensor that is used to convert mechanical motion into digital electrical signals. Now, encoders are used to keep precise track of position, speed, distance, and direction. So the components of an encoder are a light source, a pattern disk that is attached to a rotating shaft, and a photosensor. So how this works is, as the shaft rotates, this disk would rotate with it. And as you can see, it has an alternating set of opaque and clear slots. So when the light beam passes through it, it creates these series of on and off pulses, which are detected by the photosensor. And then these are used to convert them into electrical signals. The next kind of sensor that it uses is an IMU, which stands for Inertial Measurement Unit. Now, this is also used to track an object's motion and orientation in 3D space. So, an IMU measures the linear acceleration along all three axes, which is the XYZ, and the angular rotation along the pitch, roll, and yaw. And then data is mathematically combined to determine the movement, velocity, and direction of the IMU. So an IMU has three components. First being the accelerometer. This is used to measure any linear forces and acceleration that the bot experiences. It also measures the pull of gravity. Then we have the gyroscope. This is used to measure the angular velocity about the pitch, roll, and yaw axes. And the third component that we have is the magnetometer. This is used to measure the magnetic fields, and it basically establishes an absolute north reference by acting as a digital compass. So let's understand how an IMU works. So the first component that we look at is the accelerometer. It measures all the three accelerations, AX, AY, and AZ. And say the IMU is at rest. So the only force that it will experience is the gravitational force. So the net acceleration would be g, which is 9.8 meters per second. Then this is the formula that we have to calculate the roll. Roll being rotation about the x-axis. And this is how we can calculate the pitch. Pitch being above the y-axis. Then we have the gyroscope. This is used to measure the angular velocity, and this will be equal to the rate of change of angle that the wheel has rotated by. And then theta can be calculated by integrating omega with time. Now, how do we combine the things of the accelerometer and the gyroscope? So we basically make the use of both the angles and we multiply them with the factor of alpha, where alpha can range from 0 to 1. Now, this depends on how accurate each of the two components are. So, let's say our gyroscope that we're using is very accurate. You could have the alpha to be 0.9. This would mean that for the total calculation of the angle, 90% of it would come from the gyroscope and 10% of it would come from the accelerometer. So now the rover is able to measure its displacement and orientation. But how does it gain a sense of where it really is? How does it know where it is in reference to a set point? Before we delve into that, does anybody have any doubts? Okay, so we do that using odometry. Now, we know that motion sensors estimate the system's change in position relative to a known starting location. And as we continuously integrate this data coming from all of the sensors like the wheel encoders, the gyroscopes, cameras, or any other sensors that we have, we integrate all this data from them and um, odometry does this, and it is then used to calculate the linear displacement and orientation. So let's see how odometry works. So what we do here is we treat the left and the right wheel separately because they can have different velocities, right? Now the displacement of each wheel would simply be the radius of the wheel multiplied by the angle that it has rotated by. The average forward displacement of the robot would be the average of these two displacements, and the change in heading or the angle that the robot moves because these two wheels are at different velocities. This can be calculated by taking the difference in the displacements that the two wheels moved and dividing it by L. L is the track width or the length between the two wheels. And then we can represent this using a matrix. So the left-hand side here represents the current coordinates of where the robot is. This is where it was previously, and we can add the cos and sine components of the average distance to the previous coordinates to get the new coordinates. So coming back to our rover, say that it started at 0, 0 and it traveled 5 meters. So odometer says that it's now at 5, 0. Then it turns 90 degrees and travels another 3 meters. So odometry says that it's at 5, 3. But what happened here was that the rover had entered Martian sand zone. Why we have to consider this is because in the sand, the wheels of the rover started to slip. So while odometry said that yes, the rover moved all those 3 meters, what happened in reality was that it had only covered 2 meters. This brings us to challenge number three, that sensors are imperfect. As we saw, odometry was just an estimation. As long as the wheels of the rover were spinning, odometry said that yes, it was moving. So how do we correct this? This is where we bring in something called Calvin filter. So Calvin filter is basically an estimation algorithm that is used to estimate the unknown state of a dynamic system from the series of all the data that we get from our sensors. Now, as we know, sensor data can be noisy, it could be incomplete, and thus making it really inaccurate. So what Calvin filter does is it works recursively by combining mathematical and physics-based models and all the sensor data that it gets to produce one final accurate estimate. So let's look at how a Calvin filter works. First, we have the prediction step. Now, xk here with the bar on top represents the predicted current position, and xk minus 1 represents the previous position. But since it's without the bar, it means that it was the final estimate. And uk represents the data that we got from our motor commands. So we add the previous estimate and these motor commands and scale them by some factors a and b which are predetermined, to give us the predicted position. But how do we make this accurate? This is where we jump on to our second step, which is the update step. So here we calculate the final estimate by using the predicted estimate and adding a second term. Now, what this here means is, this term in the bracket here means the innovation or the residual. So it basically represents the error, which is the sensor reading minus the prediction. And then we scale by a factor k and add it to our predicted step, which we got from the first step. So let's understand this with the help of an example. Say our prediction happened to be 7, and the camera said that it was at 6. So this error term will be calculated by subtracting the 7 from 6 to get -1. And then we will multiply it with this factor. Now this is called Kalman gain. Now Kalman gain basically represents the trust factor. How much do we trust our sensors? So K can range from 0 to 1. If we know that our sensors are very accurate, then K will be closer to 1. Versus if we know that the sensors provide us with very noisy or inaccurate data, then K would be closer to 0. So in this example, we take K to be 0.8. Then the final position can be determined by adding the prediction with the Scanlon gain times the error to get 6.2. Does anyone have any doubts in this? You can raise your hands if you do.
Can you once please tell how the prediction step was calculated and what are your components?
Sorry, can you repeat that?
Once can you please explain how the prediction step was calculated? Like what A, B, and like C minus one and all that.
Okay. So basically, this is so we're calculating xk, right? Xk minus 1 represents the previous estimate, the one that we got after the second step. And we add our new movement to this. This new movement comes from the IMU or the encoder that we get from our sensor that we're using currently. And you can't just directly add them together. You have to multiply them by some factors. And these factors are predetermined. So you scale them and add them to get the current prediction. Does that clear your doubt?
Are these constants like different for each sensor or they can be near about?
These are tweaked depending on the kind of sensors you're using and how they respond to different kinds of motions.
Hello. Yes, sir. I wanted to ask how that residual is correcting the like update. Like, how is it correcting the distance?
Right. So the sensor, as we know, doesn't provide accurate data all the time. It would have some error. So this ZK represents the actual sensor reading, and we have to subtract some value from it. This is using this prediction step, and again you scale it by some factor which is predetermined. So this removes whatever inaccuracy there was in the sensor reading and gives you an error term, which is then again scaled and added to the predicted step. Does that clear your doubt?
Oh,
Uh, your voice was cracking.
yeah, I'm asking why does this work? Is it
Uh,
clear?
why why this works is if you're able to remove the error, if you're able to remove the error from the sensor reading and scale it correctly, then you will obtain an accurate result, like closer to the true value that you're trying to measure.
Okay.
See, that would be getting into too much maths. So if you're still interested, you can reach out to me after the session. Okay?
Yes.
Okay. So let's now talk about sensor fusion, which is combining IMU and Kalman filtering. So as we know, IMU provides us with continuous data, but this data happens to be flawed. So Kalman filter will mathematically merge this data from the sensor. It will cancel out any errors and give us one final accurate, drift-free estimate of the position. So let's look at the components of sensor fusion. First, we have the gyroscope. Now, this is highly responsive and it works very smoothly in the short run. But what happens is it creates very tiny errors, which over time accumulate to give us a significant amount of error. This is called the drift. Then we have the accelerometer. Now, this gives us very noisy data and it is highly sensitive to sudden vibrations. And because of the way that it is designed, it cannot physically distinguish between gravity and any sudden movement. This brings us to our most important component, which is KF functioning. Now, this predicts movement using the gyroscope and mathematically combines it with accelerometer readings. So let's understand this visually with the help of a simulation. Okay, so let me first explain what all we look at. The red line represents the gyroscope, green represents the accelerometer reading, and blue represents the Kalman filter. What we're doing here is we're trying to measure the angle that the wheel has rotated by. So as we can see initially, the red and the blue were really close together. This means that the gyroscope started with accurate readings. But over time, since the errors started accumulating, it caused drift. So it's moving farther and farther away from the actual position. This faint white light that you can white line that you can see here represents the true angle. Now, looking at the green part, the accelerometer readings stay close to the true reading, but because it's so noisy, it's hard to determine one value from all the readings that we get. So this is where Kalman filter comes into place. It combines this data from the gyroscope and all this noisy data from the accelerometer and gives us a very close estimate to our true angle. As you can see here, there's hardly any difference between the Kalman filter and the true value. Does anyone have any doubts in this? Okay. So Notebook is able to use Kalman filter to fuse together all of its input data and accurately obtain its position, right? So the encoder said that the rover was at 10,5. The camera said that it was at 8,4, and the IMU said that it was at 9,5. Now, Kalman filter takes all of these sensor inputs into account, scales them by the right factors, and then gives its best estimate, which in our case happens to be 8.9, 4.7. Now, this brings us to our challenge number 4, which is reaching the rock precisely. So, to reach the rock, how does the rover know how fast its motor should spin? What if it drives too fast and happens to overshoot the rock? Or what if it drives too slow and it takes forever for it to reach the rock? this is where we bring in control theory. So, as we know, we've lost contact with the rover. We need to be able to trust it to make all of its decisions on its own. But can it really do that? The answer to that question is yes, it can, thanks to control theory. So, what control theory does is basically allows any robotic system to behave in the manner that we want it to, but automatically. So, there are two ways that control theory can work. The first is by open loop control. What this means is that you take an input which gets passed on to the controller, which processes it and then gives us an output. So, as you can see, there was no feedback involved here. For example, say you run your microwave for 30 seconds. It's going to heat up the food for 30 seconds and then stop. Did our food reach the temperature that we wanted it to? How would we know that? Well, the answer is that we can't because it did not take any feedback. The process just stopped there. So while this is cheap and simple, there is no way of correcting any errors that could occur. This brings us to the second kind of control loop, which is a closed loop control. So what happens here is you take the input, pass it to the controller, which then gets processed, and then the output that is generated goes back into the cycle as feedback. And this keeps happening again and again. So as you can see, here feedback was involved. For example, in temperature control, say you set your AC to 22 degrees Celsius. So the temperature sensors in the AC would ensure that it keeps taking in the temperature of the room to ensure that the temperature remains at the value that we desire. So this results in our system being accurate and it ensures that our target is achieved. So how does this controller work? How does it decide what to do? Right? So the most common kind of control algorithm that we have is the PID control. Now, this might look quite complicated at first glance. So for now, let's just remember that you put in some input which passes through these three controls to produce an output that is taken back as feedback. Okay, so let's look at the first control, which is the proportional control. So let's say that we want our rover to achieve the speed of 50, and currently it is at the speed of 40. So what proportional control will do is first measure the error, which in our case happens to be 10. And then it will scale this error by a factor called kp, or the gain, to give us an output. So as you can see, the output is just a linear function of the error. So what proportional control is it basically represents our present. It measures the current error to give us a current output. Now, this is particularly helpful because the farther away that we are from our reference, which in this case is 50, the greater your output will be. So the system has more incentive to reach that reference. But a flaw in this control is that it can cause steady state error. Now, what is steady state error? Say, say the rover is at the speed of 40. Now, as you can see, the ground here is quite bumpy. So this causes a lot of friction. Now, this friction could be just right to cancel out and balance the forces that are being exerted by the motor for the rover to achieve the speed of 40. So what happens is the rover is stuck at the speed of 40. Now, since the error is not increasing, the output will not increase. And so the rover will never really be able to go beyond 40 and we will never be able to achieve the reference. This is where we bring in integral control. Now, what integral control does is it accumulates all our past errors and integrates them with time to give us the final output. So it basically represents the past because we're looking at all the errors that have occurred until now. Now, why this helps with steady state is because say we're reaching a reference, right? We're very close to it, but the error is still non-zero. So when you put that into the integral, it would give us a non-zero output, which means that there is still incentive for the rover to increase its speed and achieve the reference. And even when once you do achieve that reference point, If you add 0 to the integral, it would not change the output. So the rover will then stay at that reference. But what would happen here is that the integral could give us return a value that is beyond the reference. This causes overshooting, as you can see here. We crossed the reference and then we had to come back to stay at the reference. This is what brings us to the third kind of control. This is the derivative control. So this basically provides us with the most optimum path to reach our reference. As you can see, without this, we first overshot and then got back to our reference. But with derivative control, we will directly reach to our reference. So how this works is that it looks at the rate of change of error. As it realizes that the bot is achieving the reference, or is rather very close to achieving the reference, it will tell the motors to reduce their efforts so as to not overshoot this reference point. So it basically represents the future, where it is predicting how the motion of the rover could be. So getting back to our diagram, first we put in the input, which was a set point or the reference. We pass it through these three controls, add them all up to give us a final output, which is then used as feedback. And then this feedback and the input are used to calculate the error, and the cycle continues. So let's understand this with the help of a simulation. Okay, so here we have an inverted pendulum. This is the pendulum right here in blue, and this is the reference point where we want our pendulum to reach. On the right hand side here, we have our controls like the proportional control, the integral control, and the derivative control. This represents the start angle. So right now it's at 180, but we can change it to be whatever value that we want. So let's keep it at 180 for now. Now this represents where the pendulum is currently, and this green line represents where we want it to reach, the reference point. So let's see what happens when we put in some proportional control. As you can see, the pendulum starts to oscillate. It keeps overshooting and keeps oscillating, but finally it starts to get closer and closer to the reference point. Why it overshot was because as the error was huge initially, the output was huge. So it caused it to cross the reference and then back, and this process kept repeating. Now, let's say we introduce some integral control. Now, in this example, what integral control did was because it was integrating all the error over time, it still caused the overshooting problem to happen because since the output was so huge, it kept overshooting the reference point. So this is where we bring in the derivative control. Now you see how fast it was able to achieve the reference? This is because as it saw that it was approaching the reference, it knew that it should reduce its output. So thanks to the derivative control, we were able to take the most optimum path to reach there. Does anyone have any doubts in this? Okay, let's move on. Okay, let's now look at challenge number 5, that robots have physics. So we know that our rover is not a video game character. It's working in the real world where real forces act on it. So how does it know how much torque it needs? Would it be enough for the rover to climb a slope? What if the rock that it is trying to pick is so heavy that it makes the rover tip over? So this is where we look at dynamics and robotic systems. So the first kind of dynamics we should focus on is joint dynamics. In that, we first have friction. So there are three kinds of friction. Coulomb friction, where two solid surfaces slide on one another. Then we have viscous friction. Now, to make a rover or any bot move, it will use multiple gears and joints. And for them to move smoothly, there will need to be some sort of oiling or some lubrication. So as these joints move against one another, this lubricant would cause some viscous friction to act on them. And then obviously we have static friction. This is where you want to start your robot from rest. So what is the impact of this? It causes steady state tracking errors. It can cause jerky movements at low speeds, and obviously it leads to energy loss. Now, while we consider these factors in real life, we also need to implement them when we're making simulations. So, for example, when we're defining our left front wheel, we will put in the friction values. For example, mu1 being the forward friction and mu2 being the sideways friction. And similarly for the right wheel. Then the second factor that we have is joint stiffness. Now, depending on different applications, joints need to have different kinds of stiffness. For example, you would have a joint with high stiffness when you need extreme precision under heavy loads. You could also have brittle joints. Now, this would be used in compliant components like harmonic drives, structural materials, and donk links. And then there is something called active compliance, which is where you deliberately program a joint to be soft or springy so that it's safe for human interaction. But what is the impact of having low stiffness? Now, this can cause joint deflection, overshooting, and unwanted structural vibrations. So as you can see, if we take the example of any joint, we will have to define the spring stiffness in it. Then the third factor that we have is backlash. So what happens here is, as you can see, when we have two gears that are working with one another, there is a slight gap in between them. This is put in place to prevent any jamming or overheating. But what problem this causes is, say you connect the first gear to a motor and you reverse the direction of motion. Now what would happen is, while the first gear would immediately respond to that movement, the second gear, because of the gap, would take some time to respond to this. So this can lead to problems like positional accuracies, oscillations, and instability in feedback loops. Okay, the second kind of dynamics that we study is wheel ground interactions. Now, this here is an example of a skid steer. So a skid steer is a vehicle that has four or more fixed wheels locked in parallel alignment. So anytime that you want to turn this vehicle, you cannot just move the front two wheels as you would normally in a car or a truck, right? So how it does make a turn is by physically dragging its tires across the ground. For example, in this animation, you can see that the skid steer is turning to the right. So a way that it could this is by keeping its right wheels fixed in place and rotating only the left-hand side of the wheels. So this would cause it to turn in its place, which allows for zero radius turn. The second kind of wheels that we have is mechanism wheels. Now, this is where it's a special kind of wheel that has passive rollers oriented at a 45-degree angle to the plane of the wheel. So, as you can see, this allows the bot to move front and back, sideways, and basically in any direction. And it can rotate by any angle ranging from 0 to 360 degrees. Okay, let's now move on to challenge number 6, which is collecting the rock. So the rover is able to reach its target, but now it must grasp that rock. So which actuator should it use? How much torque will be required? And how accurately must the arm move to retrieve this rock? So we have different kinds of actuators that the rover could use. The first kind is the DC motor. Now, how this works is that its speed is dependent on the applied voltage and its torque is dependent on the current. Now, these motors are very simple to use and inexpensive, and they also have good speed range, but they have low precision and maintenance is required because of the way that its components function. So we have the second kind of actuator, which is a BLDC motor. This is a brushless motor, and unlike the case of DC motors, it uses electronic commutation instead of mechanical brushes. Now, this makes it highly efficient. It has very high speed capability and also a longer lifespan because it doesn't require the kind of maintenance that a DC motor would. But it is more complex to control because it needs to be run with an ESC, which is an electronic speed controller, or a motor driver. The next kind of motor that we have is a servo motor. Now, these are designed to go to a commanded position and then hold that position. So they have high positional accuracy. They're very easy to control and they're used in applications where they're required to move only for a limited range. So the most common kind of range is 0 to 180 degrees. And the fourth kind of actuator that we could use is a gearbox. So a gearbox is a mechanical transmission that is attached to a motor and it basically changes the relationship between speed and torque. For example, a reduction motor increases the output torque by decreasing the output speed. So gearboxes provide us with high torque. They're very precise and have controlled motion, but they can be heavy, expensive, and they obviously lead to efficiency loss. So, what are the different applications and which actuator would be compatible with them? The first kind that we have is wheel turbo. This is where we would use a DC or a BLDC motor paired with a gearbox to provide enough traction and for it to be efficient. Then in drones, we use BLDC motors because of their high speeds, they're highly efficient, and they have a very low power to weight ratio. In heavy lifting applications, we would use the appropriate motor paired with a gearbox. And in a robotic arm, we would use either a servo motor or a BLDC servo for accurate joint positioning. So let's review the criteria for a robotic arm. First, it has to move to a specific angle. Then it has to stop there precisely and hold that position. It then has to lift the rock and resist any disturbances. So, which motor of all the ones that we discussed would check off all these criteria? That would be the servo motor. So, let's break down where which joint would use which kind of motor. So, in joints where you require high precision and high positional accuracy, for example, the camera, the wrist, and the gripper, this is where we would use the servo motor. And in joints that require high speed and high torques, for example, the shoulder, the elbow, and the wheels, this is where we would use a BLDC motor paired with a gearbox. So that's it. The rover was able to cover all of its challenges. It successfully perceived its surroundings by using its sensors. It was able to estimate its position using odometry and Kelvin filtering. It was able to decide how to move and act using PID. It was able to travel and pick up the rock using its actuators. And it survived the real world by using dynamics. Okay. Does anyone have any doubts? All right. So let's now look at a little prerequisite for the upcoming sessions. So you all will be learning ROS, and I'm sure you will build some amazing projects. But when you go to share them with your friends, you find out that it's not working on their computer. Now, why does this happen? This could be because of multiple reasons. Now, different systems have different setups. They could have different dependencies, different versions, and different libraries. So before we work on how we can solve this problem, let's first understand how a machine works. So we have the application, the kernel, and the devices. So a kernel is basically an intermediate between the software and hardware part of your machine so that the two can communicate with one another. So we have the CPU talking to the kernel, which then talks to the application. This will use some memory and also the other external devices connected to the machine. So how we can solve the problem is why not instead of sharing just the code, we share everything else, all the libraries, the dependencies, and the kernel associated. Now this brings us to the concept of isolation. If you want multiple systems to work on a singular machine, you need to make sure that they do not interact with each other because this could be a breach to security. You could have unnecessary data sharing, or it could interrupt the workings of systems, and this would again lead to problems. So you basically want to isolate all these systems. So there are two ways of doing this. You could use a virtual machine or a Docker. Now, what is a virtual machine? It's the software version or the software simulation of a physical computer. So what it means to have a virtual machine installed onto your machine is that the virtual machine represents an independent computer. So using virtual machine, you can run multiple operating systems on a singular physical device. Now, what is a Docker? A Docker is a tool that helps us run applications in containers. So, what is a container? A container contains the code, the libraries, and dependencies associated with an application. It is basically a mini computer. So, what a Docker helps you with is, for example, if you want to run a ROS container. So, you can package all of its dependencies, its settings into a singular container that can then work on any system. So, you can now ship this container from one system to another and it can work anywhere. Now, what is the difference between a virtual machine and a Docker? So first we start with the hardware, then we have the host kernel. Then for virtual machine, we have hypervisor, and for Docker, we have container engine. Uh, so what the hypervisor does is it acts as an intermediate between the kernel and the different virtual machines installed onto the computer. The container engine does the same job, but between the kernel and the different containers. And then each virtual machine will have its application, and each container can have its application. So what is the difference between the two? Now, a virtual machine is basically an independent computer. So it will have its own OS. So each virtual machine that you have installed onto your computer, let's say you have two virtual machines installed. So you will basically have three operating systems in your computer, one for each of the virtual machines and one being the OS of your own computer. So while this is beneficial in the sense that since each virtual machine is its own independent computer, there will be no sharing of data, no security breaches between the different virtual machines. But how this can be a disadvantage is that it is very heavy. Heavy in the sense that it will use up all of the computer's hardware resources and it consumes a lot of memory. So, how a Docker differs from this is that it uses the operating system of the very computer that you've installed it on. So you could have multiple containers, each containing applications, and they will still only use up some part of your memory because in the end, it is still using the operating system of a computer. Now, let's look at Docker in little detail. So we have the image and the container. Now, an image is basically a blueprint of the application that you're trying to run. So it will contain all the codes, libraries, and configurations related to that application. And the container is what comes into existence when you run the application. So while an image is static, meaning it always exists, the container only comes into play when you run that particular application. So what are the applications of this in robotics? You can run simulations like Gazebo and ROS in isolated environments. You can share robotic algorithms and demos with your friends. And you can deploy robotic software on cloud-based systems for remote control. So let's now look at how we can install Docker. Okay, so I'll show you the steps to installing Docker. Um, you have to follow these with me, okay? Okay, for all the Windows users, first open your PowerShell as administrator. Let me repeat, you have to do this with me, okay? All right. So the first thing that we have to do is install WSL. Now, to check if you already have WSL installed, you type in this command, and if you do have it installed, then it will show you the list of all the distributors. Since I have it installed, it shows me this. But if you don't have WSL, then it's going to return nothing. So in that case, you have to type in the command to install it and then hit enter. So I hope everyone has typed this. Okay. For the Mac users, what you have to do is you have to first install a DMG file. This is for only the Mac users. So you type in this link into your search engine, Xquads 2.8.1, and press enter and click on the first link. And then click on this here and download the DMG file. Okay, so now let's get to installing Docker. So just type in Docker install, and depending on if you're using Windows or Mac, type that in next. So I'll show what to be done for Windows. Then click on the first link and then click on the first option that you see, Docker Desktop for Windows x86-64. Like Mac users also do the same. Click on the first option that you find. If you've reached here with me, then can you put a thumbs up reaction? Okay, this process will take a few minutes, so I'll give you a few minutes to install. Once you're done, just put a thumbs up reaction. And if you have any doubts, you can ask. Is everyone done with the installation? Could you react with a thumbs up or a thumbs down? For those of you who are raising their hands, do you have a doubt? Okay, so let's move on. If you're not done with the installation, we will send the instructions later and you can do it later on. Okay, so once you do install Docker, this is the screen that should pop up. As you can see, we have different tabs here. We have the containers that shows us the list of containers that we have on our Docker. We have the list of images and so on. Now, on the right hand bottom side here, you can see the option of terminal. So what we're going to do is we will install the image for the Docker container. We'll share all the details later. All these links and commands will also be shared. Okay, so We put in this command and press enter. Now, for those of you who are doing this for the first time, this will take about 20 to 30 minutes. Since I already have it installed, it didn't take me that long. Okay, so now how do we come about to run the ROS container, right? So what we do is in actions here, we first press this button to start the container. And then there are two ways of accessing it. First way is by clicking this under the ports. So this will redirect you to your web browser. Just a second. Okay. So it will direct you to this page. Now another way of accessing it is by typing in localhost and then whatever number it shows under the port section in the Docker page. So the number was 6080. Press enter and it will open you to the same page. Okay. Then we click on connect and on terminator. Okay. So this opens up the terminal and then we can type in whatever commands that we want to run this container. So let me just show you a few examples. So this will show you the list of all the distributors that you have installed. So it's showing details for Ubuntu. Then right. Then the particular ROS distributor that we're using is Jazzy. And we can also open up a gazebo simulation. The particular one that we're opening is the shapes file. As you can see, we have different shapes here, and we can then use to work with gazebo, and we can open multiple other kinds of simulations. That was about installing Docker and running its containers. Let's now look at what all we'll learn in the upcoming sessions. So, using everything that you learn in the upcoming sessions, you'll be able to build some amazing projects like the line follower, spatial signal mapper, rover on Mars terrain, controlling port with lighter integration, drone in forest, pickup in place and many more. So that was all for today's session. Hope you enjoyed. Continue solving your assignments and stay tuned. Thank you. If anyone has any doubts, they can ask now. Does anyone have any doubts?